we will discuss the standings modification of Vogel's IPR. As we know, the original Vogel model is limited because it doesn't account for changes in permeability of wellbore damage. To solve this, Standing proposed a procedure to adjust the curve whenever we have a non-zero skin factor, meaning when the well is either damaged or stimulated. We express this change through the productivity ratio, as also known as flow efficiency. To understand this modification, we must first define flow efficiency, or FE. Looking at equation 2.41, FE is the ratio of ideal drawdown to the actual drawdown. Here, the PWF represents the ideal flowing pressure we would have if the well had no damage. Alternatively, as seen in equation 2.42, when we calculate Fe using the skin factor and the reservoir geometry, simply put, Fe tells us how much of our reservoir's potential we are actually capturing. Now, let's look at the math. By integrating flow efficiency into the Vogel relationship, we get equation 2.43. This allows us to express the flow rate ratio in terms of ideal pressure ratio. It's important to know the term Qmax at Fe equals 1, which represents the maximum potential flow if the well had zero skin. To make this applicable to or measure that data, we use equations 2.44 or 2.45 to relate our actual flowing pressure to the ideal pressure. How do we actually build these curves? The process follows five logical steps. First, we select a flow efficiency based on our well test. Second, we define a range for our pressure ratio from 0 to 1. Third, we calculate the adjusted ideal pressure for every point. Fourth, we determine the flow rate ratio using the modified Vogel equation. And finally, we plot the results to see how the well's performance shifts according to its condition. This flowchart summarizes the entire logic. We start with our input data, skin factor, test pressures, and reservoir conditions. We move through the four main processes as calculating Fe, assuming pressure range, finding the ideal pressures, and determining flow rates until we can plot the final IPR curve. If we need to perform a sensitivity analysis, for example, to see the effect of a future stimulation, we simply iterate the process with a new Fe value. However, we must be aware of certain mathematical limitations because standing method is a reference to an Fe of 1. Highly stimulated wells with every high drawdown can sometimes result in a negative ideal pressure. This creates a mathematical inconsistency in the model. On a more practical note, we use the fall of increase, or FOI, or FOI. This is the ratio between the flow efficiency after a treatment and the efficiency before it, which help us measure the success of the stimulation. Visually, the impact of a skin factor is striking, as you can see in this chart. When a well is damaged with an Fe or zero point 0.5 or zero point 0.3, the curve shrinks to the left, indicating much lower production. When the well is stimulated, this means Fe about 1. The curve expands significantly. Note the red dashed area, that is the mathematical inconsistency zone. I had mentioned earlier, where the where we must be careful with our interpretations at very high drawdowns. Um, Practical application and productivity improvement. The real power of this method is in forecasting. By establishing a base case with current test data, we can calculate our wall's ideal potential. Then we can run sensitivities by assuming a new and improved FE values. This allows engineers to quantify exactly how much production will increase after a stimulation. This provides a clear financial justification for workovers or investment in the well. Finally, let's look at a real world example. We have a well with a reservoir pressure of 2085 psi and a current FE of zero point 0.7. Based on a test at 7065 psi, the well produces 202 barrels per day. By applying our equations, we calculate an ideal maximum flow rate of about 1097 barrels per day. And if we stimulate this well to FE of 1.3, we can see in the table in the graph how the production potential nearly doubles across all pressure levels. This clearly illustrates the impact of improving this flow efficiency.